Hey everybody, I want to talk to you about the most important distribution in all of statistics, the normal distribution. It's called by some other names, the Gaussian distribution. You might have heard of it as the bell curve. They're all the same thing. So let's see what they look like. Where did I put it all on the whiteboard? Oh right, I didn't go back to the beginning. All right, so there's my first screen. So normal distributions, they are by far the most important of all the distributions. So for a couple of reasons. Now, I don't want to ramble too long here, but there's a couple of reasons why normal distributions are the most important. Number one, and the less important of the two reasons, is that many things are normally distributed. It is by far the most common thing that you will find in nature, or by far the most common distribution that you will find in nature. It is also like where it comes from is actually a really interesting, like 100-year-long story about astronomers and them trying to measure the position of stars accurately. And when you're doing that, when you're doing that with hand pointed telescopes, right? There's always errors, and so you have to figure out how to account for the errors. And there's this long history that eventually leads to the normal distribution being the answer to how the errors are distributed. And it's sometimes called the Gaussian distribution because of Carl Friedrich Gauss, possibly the greatest mathematician of all time, and the guy who figured out what the formula for the normal distribution is, which I will show you when we get to the Desmos part of my presentation. So it's defined by its mean and standard deviation, and I'll show you what I mean by that in just a second. Like I said, it's the famous bell curve you may have heard of, and I will talk about the empirical rule in just a second after we go look at the distribution itself. So here is a classic, like the basic normal distribution. Now, when I say the basic, there are an infinite number of them because if you change the mean, it changes its shape. It's still kind of the same shape, but if you change the mean, it slides around. And if you change the standard deviation, that actually changes its shape, but it's still sort of the same basic shape. And I'll show you what I mean. So I've got my mean set up as M and my standard deviation set up as S. And so if the mean changes, that move, oh, I've got it zoomed way too far and you can't possibly see that. Let me do this up to like 5 so I can move it reasonably slow. Like you can see when I change the mean, all that does is sort of move it around. And one thing I do want to point out is that normal distributions go infinitely to the right and left. It's just that the probabilities get really small as you get well away from the mean, right? You can see it's never quite hits the axis. It looks like it might be hitting there, but if I zoom in, it's not touching. Right. And if I get really far, like I can keep going, I can do this forever and it'll never get there. Right. So it never quite gets to probability of 0, but at a certain point, and that certain point is usually 3 or 4 standard deviations where people start kind of neglecting the area past those points, or not neglecting, but like it gets very small past that. 3 or 4 standard deviations from the mean. Oh, and I should mention that standard deviations are like a thing that you have to think back to about standard deviation is that standard deviation is a distance, right? It is an average distance from a mean. So it's just some number. Well, that number defines how spread out your distribution is. So if I make it bigger, that will spread my distribution out more. And if I make it smaller, that will make it get spread out less and more peaky in the middle, because as with every distribution, the area under this thing is 1. It's exactly 1 at all times. So when I change the width, it also changes the height. So the area is still 1. All right, and so you can see you can get kind of flat, but if I zoom out enough, you'll see that it goes towards 0, just like every other version of this. And this is what I meant by it's kind of always the same shape, right? They're not like precisely the same shape. Some are taller or shorter, but it's kind of all like, it's sort of all like chairs, right? They're different kinds of chairs. They look different. They're different sizes. They seat different people or different amounts of people, but they're all kind of chairs, right? And normal distributions, same way, right? There's fatter ones, there's taller ones, but they're all kind of the same bell curve, the same basic bell curve shape. So there's one other thing that I want to mention about normal distributions before we go any farther, which is the empirical rule. So the area within one standard deviation of the mean is about 68%, within 2 standard deviations about 95%, and within 3 standard deviations it's about 99.7%. So notice that it's 0.3% outside of 3 standard deviations, which is, you'll note, very small. So when we go here, we can see that here I've got an empirical shader, right? And so it's here's within 1 standard deviation, you can see it's about 68%. I'm going to make this exactly one that's going to bother me there. Within 1 standard deviation. So in this case, the standard deviation is 1. So, and the mean is 0. So when I'm within 1 unit of 0, I get 68% of the area under the curve. And when I am within 2 standard deviations, so between -2 and 2, I get about 95% of the area. And when I'm within 3 standard deviations, between -3 and 3, I get 99.7%. And it may even look like there's nothing, there's like, this is just shaded out to infinity, but it's not. You'll notice that I've stopped the shading at 3, it's actually blank after that. Yeah, and there's so little area there that you almost can't see it. So that's your empirical rule. You don't really need to memorize that. Write it down at least, but you don't really need to memorize that, because the way we're actually going to calculate areas under normal distributions is with your calculator or computer, because there's not a good way to do it without. Well, that's not true. There is a way to do it without. We're not going to do it that way. It involves looking things up in tables. Calculators are just way better. So we're just going to do it with calculators and computers, because that's the way everybody does it now. Nobody really uses the tables anymore. Just as a little side note, your stats book, the Open Stats statistics book, is the first one that I have ever seen that doesn't include the table for normal distributions that you would use to do this calculate, which I think that's good. I think that's a positive thing. All right, so there you go. There's your basic normal distribution. I'm going to get to an example. Where is my whiteboard? There's my whiteboard. All right, so let's look at the example. So among many, many, many other things, heights of American women are approximately normally distributed with a mean of 64.5. Notice this is a mu. That's I know it looks like either a fancy U or a fancy M, depending on how you're looking at it. It is a Greek lowercase m. It is the population mean, right? Population average, if you recall from way back in topic 1. And population standard deviation of 2.3, and these are both in inches. And I want to find these basic probabilities. Find the probability that x is greater than 66, that x is less than 68, and that it's between 60 and 64. So this is 66 is 5'6". So those of you who are maybe not Americans, there are 12 inches in a foot. And so 5 feet is 60 inches. So this right here is 5'6". This is 5'8". This is 5 feet even, and 5'4". So this is really asking, what's the probability that a randomly selected American woman is taller than 5'6"? That's what this question says. So it says what's the probability that she's less than 5'8", and this one says what's the probability that she's between 5 feet and 5'4". So we're going to go find all those probabilities, but first I am going to draw them. One of the things that you want to get really, really in the habit of is drawing your normal distributions. I bring this up because the calculator asks you for a bunch of stuff, and I'll show you how to do it in Sheets as well, and then the commands are the same in Excel, I think. The computer or calculator asks you for a bunch of stuff, and to know what to put in, it is incredibly helpful if you have drawn your distribution, especially when you're just getting started with it like we are now, right? So at the very least, draw your distributions for the first, I don't know, 2 dozen times you're doing a problem. I can't even tell you how many normal distributions I have drawn over the years, probably in the thousands at this point. So many. It's really not as much of a hassle as it seems like, just draw them. Okay, so I want to answer the question, what is the probability that X is greater than 66, or that the randomly selected woman is at least 5 feet 6 inches taller. I guess technically taller than 5'6", but again, like I discussed in the uniform distribution video, this is a continuous distribution, greater than and equal to, give you the same probability. So what I'm going to do is I'm looking for the probability that she is greater than 5'6", so bigger than 66 inches. I have drawn my mean in the middle of my distribution, which is where it goes. And I'm going to put on the number that I'm looking for. And I'm going to put it on the, I'm going to use this as like my anchoring point. This thing down here is a number line. So don't put the 66 over here because it doesn't go over there. 66 is bigger than 64.5. So put it over here. Don't worry too much about drawing it precisely. This is just a visual aid. This is not going to, like, being imprecise with this is not going to hurt you in any significant way. So I'm going to say this is 66 right here. 66 would probably be whatever. This is pretty close. Let's shade that in. So I was looking for the probability that she was greater than 66. So I'm going to shade in the area to the right of 66, and that is the thing that I'm looking for. Now, the command in your calculator is this one, although you probably have a screen like the one I'll show you in just a second. But if you don't, this is the order the things go in, and I'll show you what I mean. So let's. So here's what I'm going to do is I'm going to go to the calculator, find normal CDF. It's in second bars or distributions, same place as all the other ones, and then I'm going to put in the left boundary of the area that I'm looking for, the right boundary of the area that I'm looking for, which is in this case infinity. We'll see how to put that in just a second. The mean of the distribution, so 64.5, and the standard deviation of the distribution, which is 2.3. One thing I do want to point out, this number, 2.3, is not a number on our distribution. I will have people try and put it over here, or they'll write it as like a label or a bunch of other things. None of that. It's not any of those things. This is a distance from, it is an average distance from the mean of all the points in the distribution, which is not a number that goes on the graph. I put it off to the side because that's a thing we're going to need in the calculator. So we need to know it. So I wrote it down, but it's not a thing that goes on the graph. All right, let's go see what the calculator looks like. So calculator, that it does not help if I click it, but don't share it because then you can't see. Okay. So I want to find the area to the right of 66. So that is going to be, I'm going to go to second vars, so distributions, same place as all our other distributions. And we've got normal PDF and normal CDF. And we are basically, I think, actually never going to use normal PDF. Normal PDF gives you the height of a point on the graph of a normal distribution. And we will never care about that. The thing we care about is area, because probability is area, and we're going to use this to calculate probabilities. So that is CDF, cumulative density function. So normal CDF, and I want the lower bound, the upper bound, the mean, and the standard deviation. So that is those things that I just said a second ago. We're on the whiteboard here. I want the lower bound, the upper bound, the mean, and the standard deviation, right? I call them A, B, mu, and sigma. Right, and that's what your calculator is looking for you to put in here. So my lower bound was 66. That was the left end of the area that I'm looking for. The upper bound was infinity. Now, you can put in the biggest number that your calculator will accept, which is 10 to the 99th power, or if you have a TI Inspire, I believe it is 10 to the 999th power. And that is the best infinity that you could get. But it probably doesn't make that much difference. It's not going to be that much different than if I put in like 100. And I'll show you what I mean. So here's the biggest number my calculator will accept. It's 10 to the 99th power, which you can do with the EE button. I don't know why it's capital E here, but this will give you 10 to the power of 99. This is your calculator symbol for scientific notation, in case you were not aware. Excuse me. So this is as close to infinity as our calculator will accept. The mean of our distribution was 64.5, and the standard deviation was 2.3 inches. All right, so we're going to paste that in. Notice that what it gave me was A, B, mu, sigma, the same order that I put it on the other on the whiteboard screen. If your calculator didn't give you that screen that I just had, which the old ones don't, it just gives you normal CDF left parenthesis. you have to type that in. You have to type it in that order, A, B, mu, sigma. That's actually how I got used to doing it. That new screen is pretty nice for me, but this is the way I learned. 25.71%. Sure, that seems reasonable. I'll go ahead and write that down. So this says that American women, that about a little over a quarter of American women are 5'6" or taller, which sounds about right. Right, that's a reasonable number. And you might think to yourself, well, wait, it feels like more than half the girls I know are 5'6". Keep in mind that this is all American women, including little 80-year-old grannies who've shrunk quite a bit. And so they're included in this. And so the fact that you know a bunch of young women who are at their tallest means that you probably know a bunch of women in this area of the graph. So don't generalize your experience to the experience of all people. Okay, so we got where did I say 25.71. So this is about equal to 0.2571. I kind of default to 4 decimal places as being quite accurate without being excessive, right? I don't want to read a number that's 20 digits long. I'm just gonna mentally cut it off after the first couple places anyway. You could certainly do more if you wanted. I think 4 is pretty good. Sometimes it won't be. Sometimes we'll need a lot of zeros in front or whatever. But yeah, if you're just looking for a default number of decimal places, 4 is a good choice. All right, so that was greater than 66. I actually do want to show you what that looks like in an accurate picture that's not mine, or that's drawn by a computer rather than me. So the mean here was 64.5. The standard deviation, that's fine. The standard deviation was 2.3. And let's go see what that looks like. I'll zoom out and head over there. Zoom back in. So you can see, since our standard deviation isn't 1 anymore, it's 2.3, this thing is much shorter and flatter than it used to be. And so the area that is within 1 standard deviation, instead of being within 1 unit now, is within 2.3 units of 64.5, right? So this upper end here is 66.8 and the lower end is 62.2. Right? And so that area in there, but there's still about 68% of the area in here. Yeah, that's kind of all I wanted to show you. What we were looking for was this, our observation. I'm going to make that, we say, oh God, I can set it somewhere, right? SM over S. Why can't I set it? Oh, there it is. Yeah. Sorry. This was 60. What was it? 66. Yeah, there we go. And we're shading to the right. So this area that I found right here was 25.7%. Sorry, I forgot how my model worked for a second there. I haven't used this in a while. I wrote this thing, so you'd think I would know how it worked a little bit better. Yeah, but this was 25.7% was this area on up. Okay, back to the problems. We'll show you how to do this in Sheets in a little bit. It's a little less convenient. This is one area where your calculator is actually nicer than Sheets or Excel. Okay, I want to find the area where X is less than 68. So we're going to draw that as always. Go ahead and erase here. Whoop, no, computer, erase. All right, there we go. Back. Oh no. Sorry, I'm gonna fix this real quick. That's not as nice as my last one, but whatever, you get the idea. So we're looking for less than 68 here. So 68 is over here somewhere, 68. And we are looking to shade to the left of it because I want less than. And this should be a pretty big number as expected, right? If the average height is 64.5 inches, or 6'4.5", then we would expect most women to be less than 6'4.5", 5'4.5". We would expect most women to be less than 5'8". So it would make sense that this probability would be pretty big. I'm going to do normal CDF of left end, right end. So the left edge of the area we're looking for, the right edge of the area we're looking for, mean standard deviation. So in this case, the left edge of this area is at negative infinity. And you can put in negative infinity if you want. In a sense, though, the left edge of this area is actually at 0, right? Because the effective minimum height is probably much bigger than 0, but like you certainly couldn't have someone with less than 0 height. And we'll do it both ways to make the point that it doesn't matter which one you choose. They're both fine. But I do like it when students are thinking about, well, wait a minute, if this is supposed to represent the height of a person, I can't have negative infinity, right? That's not a height. So anyway, let's do it and see how it works. So I'm going to go to bars and normal CDF. Now my left edge, the left edge of the area I'm looking for, I said it was at negative infinity. So let's put that in. So I'm going to put in E99, E99, negative infinity. And it goes up to 68 inches. And the mean and standard deviation are the same distribution. Paste that in, get some big number. Yeah, 93.6%, 60%, which is pretty much everyone, right? Very few women are over 5'8". About, what is that, 6.4% of American women. So not that many. Yeah. So before I write that answer down, I want to make this point. Let's do the same exact thing, but I'm going to use 0 as my lower bound rather than negative infinity. And we should get precisely the same number. And lo and behold, it's the same number. And you might say to yourself, well, wait a minute, those can't be the same. You said this goes all the way to negative infinity. How can these two numbers be the same? And the answer is, these two numbers are not the same. They're just the same for the first 10 decimal places, which is all your calculator shows. So you can see why we don't care about the area in the tails that are far away from the center. It's so small, it doesn't even show up in the calculator, right? This whole thing, like using this normal distribution for to approximate the height of American women, is all an approximation and a model anyway. So expecting more than 10 decimal places of precision is irrelevant. Anything past the first couple doesn't really matter. So yeah, so this is, you get the same thing either way. Oh, and I wanted to make the point that if I had used 100 here instead of E99, it would do the same exact thing, right? If I did 66 up to 100 with 64.5, mean of 64.5, standard deviation of 2.3, we would have seen exactly the same thing happen here, where the first 10 decimal places are all the same. I don't even know where the first decimal place that it differs is, but it's not in the first 10, and so I don't care about it. So whether you use infinity or just some number that's significantly bigger than your mean doesn't really make too much difference. Feel free to do as you choose. I honestly usually type in like 10,000 or something like that, rather than doing E99, because I hate hunting around for the E key and the second key. I just type a bunch of ones and zeros. Anyway, moving right along, we got about 93.6% of American women are shorter than 5'8". So let's go ahead and write that down. That is the previous page. About equal to 0.9360. And by the way, if you are using 4 decimal places of accuracy, it's actually better to write 0.9360 than it is to write 0.936, right? And those are clearly the same number. So why is that better? It's better because what you're saying is, this number, I know it's not like a 9 or whatever, right? You're saying what this number is. So you're still telling the reader, I have 4 decimal places of accuracy here. It's just that the fourth one is a 0. So in statistics, that's not going to matter hardly at all. But when you get into the sciences, they'll care. So they'll really care about significant figures. So I'm not going to worry about it too much, but just a heads up. If you mean 0.9360, write the 0, even if it's technically the same number. Okay. And then the last one is the easy one. I'll just do the probability that the randomly selected woman is between 60 and 64 inches tall, so 5 feet and 5 feet 4. This should be a relatively large percentage because 5'4" is right where the middle is. That's where it gets tall, right? So let's go shade that in on the graph here. Eraser. Let's see here. Can I be precise enough to not erase my thing? Ooh. All right, good. I got it this time. Success. All right, so 5 feet to 5'4". No, that is, it will not accept that until I turn the whiteboard off. 5 feet to 5'4". We're just like right here. That should be less diagonal. 60 to 64. It's right there. Okay, and so that area that I want to find is this area right here. And so you can see that's going to be relatively large. I'm going to expect it to be, 40%, something like that, maybe 35%. I'm just guessing here. Let's go look at that on the calculator. So calculator, we're gonna do normal CDF. Lower bound is 60, upper bound is 64, and the mean and standard deviation are the same. And we get, 39%. I was relatively close. All right, so 38.87%. Let's go write that one down. Right here. Seven, was that the number? Whatever, you get the idea. So there you go. That's pretty much how it works. Now, let me go talk about how to do this on Excel and Sheets. I'm going to show you in Sheets, but I believe the commands are exactly the same in Excel. They might put a period in a different place or whatever, but look at the help file. They're almost exactly the same, if not exactly the same. Where is my? Oh yeah, I had it on here. Here. Okay. So the command that you want is this one, norm.dist, and they want not the same thing that your calculator puts in. They only want one number. They, instead of saying like put in the left edge and the right edge and the mean and standard deviation, they're saying just put in this number here, an X value, and then the mean and standard deviation, and then say whether it's cumulative or not, just like it was doing in the other distributions. Cumulative means you're using normal CDF. Not cumulative means you're using normal PDF. So for us, this will always be true. We're never going to have this thing set to false when we're doing normal distributions. So here's what it's asking for. It's asking for the mean and standard deviation. So let's change this to what we had here. So the mean was 69 or 64.5, and the standard deviation was 2.3. And so the first one we found was 66. Right, it's 5'6". So we do that. Let's enter on that, and it gives me this, which you might notice is not the same number that we had before. However, what it is doing, it is giving you excuse me, stumbling over my words there. What it is doing is it is giving you the area to the left of the number you put in. So this is giving me the area to the left of 66, which you might recall is not what we wanted. We wanted the area to the right of 66, right? Let me just switch over to here. Sorry, to here. Yeah, we wanted this area to the right of 66, but it's not giving me that. It's giving me this. It's giving me it's giving me that area. Right? It's giving me the area to the left of 66 when I wanted the area to the right. So you have to subtract from 1. Like you have to do this subtraction yourself. It won't do it for you automatically. And it doesn't, as far as I know, it doesn't have an option to put in like left edge, right edge. It's the only thing you can do is put in that number and then it'll give you the area to the left, even if that's not what you wanted. So that's what I meant by your calculator is better than the computer in this regard. It's better than Sheets or Excel. Excel does exactly the same thing, by the way. Yeah, so you have to do the subtracting yourself, right? If I did this equal, let's see, I would have to remember beforehand that I wanted the area to the right, and to do that, and that is the number that we got, right? 25.71%. So if you're okay doing the subtraction, the Excel and Sheets work fine. Like there's nothing wrong with them, except that they could be more user-friendly, basically. Yeah, if you want the area to the left, great. If you want the area between two things or between two numbers, what you have to do is this. I'm going to demonstrate with a picture because that's the easy way to do things. Like let's say I wanted something like this. What I would have to do is I would have to do two of these things. One of them would be the area, oh, I have to turn my wiper off. One of them would be the area to the left of 64, right? So I find all of this and the computer gives me all of that stuff. And then you have to tell it to do, then you have to tell it to subtract off the area to the left of 60, right? To chop that stuff out. So the only thing that you're left with is the area that you wanted. So you have to do that manually if you're doing this in Excel or Sheets. Not the biggest deal, but a little less convenient than it could be, for sure, right? And your calculator will do that for you automatically. It's actually quite nice. And in fact, your calculator even has one more function that it will do. That was not the button I meant to hit. Let's hit the calculator, share the calculator button. Is if I do normal CDF, it should let me draw the distro. Oh, wait, it does that with normal, right? I'm forgetting now. No, it doesn't. What? What the heck? It'll draw the other ones. That's really weird. Like if I go to, I don't know, chi-squared. Wait a minute. Oh, this is still normal CDF. My bad. Sorry. All right, I'm getting off on a bit of a tangent here, but there's some way to make your calculator draw the distribution that you are looking at. Where is it? Oh, it's here. Here's where you go. Draw. Okay. So this is where it will shade in what you're looking for. So I could shade in lower bound of 66, upper bound of one and a bunch of zeros, mean of 64.5, and a standard deviation of 2.3. Color it blue, that's fine. And it will not show me the area because it's not looking at the right area on the graph. You have to zoom for it. Does zoom stat work? I don't think so. No. We're gonna have to zoom function. That's one of the things in here, right? Zoom fit. Does that work? No. Maybe we'll have to manual zoom. So calculators maybe a little bit less convenient than I was hoping for. Here, let's go ahead and do this. We'll go from 59 to 70. That all looks great. No, that actually doesn't look great. Sorry, this is gonna have to be like -1. -1 is too much. 0.1 up to like 0.3. Graph. We'll do it now. No, because it's not drawing it again. All right, so if I go back and do it again, oh, that's a little bit awkward. There we go. Now we can see it. Fantastic. Super easy. Couldn't be simpler. This calculator's a little annoying too, but you can see that it draws the graph that I had in Desmos. Right here somewhere. Right. There's my Desmos graph. You know what I should do is I will put a link in the description of this video to my Desmos file, or to my Desmos thingamabob here, so that you can have this. One of the things that I have found is that it's actually quite hard to find a good normal distribution sketcher on the internet. It's harder than you might imagine. I thought it would be like one of the things that was easiest to find on the internet, and it's not. So I made one. Yeah, so I will put a link in the description of the video to this. Although I have never tried to link in the description before, but there should be a way. I know there's a way because every YouTube video does it. but I don't know it yet. So anyway, I'll figure that out. There you go. That is normal distributions. Now, it turns out there are tons more things to learn about normal distributions, like kind of a lot more things that we will learn coming up. But for now, just finding areas under normal distributions is fine for us. We will eventually learn how to find percentiles, and then we'll learn why normal distributions are so important when we get to the central limit theorem, which is topic 7. It's coming up very soon. Central limit theorem is super important in statistics and uses normal distributions, which is that's actually why statisticians use them so much. Yeah, and I think all that said, that is about all I wanted to say about normal distributions. So I will go ahead and stop talking now, and I will see you guys in the next video.